Thank you. Thank you very much. So I'm going to talk about the compatibility of local and global Langlands correspondences for GLN. And such a thing is desirable because it generalizes, say, the compatibility of local and global class field theory. And also, it can be useful for proving modularity lifting theorems. So I'll start with just an introduction. So we'll take L to be a CM field, and we'll fix for some prime number L an isomorphism of QL bar with C. And we'll take pi to be a cuspidal automorphic representation of GLN of the adels of L. Such that it's conjugate self-dual and regular algebraic. So to such a pi, you can associate a Galois representation. So let RL of pi be the representation of the Galois group of L into, say, GLN QL bar associated to this pi. Then I want to state the local global compatibility result. So theorem, let Y be a place of L above some prime P, which is distinct from L. Then the Wedelin representation associated to the restriction of RL of pi to the decomposition group at L. Frobenius semi-simplified is isomorphic to the local Langlands image of pi at the place Y. So this is the local Langlands where we use a certain normalization, say the geometric normalization. All right, so this is the theorem that I want to talk about today, just to talk about kind of, sorry? Degree 1 prime over.
This is the local Langlands or GLN?
Yes, it's the local Langlands for GLN.
So your prime is over the CM field or the vector real sector?
Y is, yes, it's a place of the CM field.
Oh, okay.
Is that? Okay. So we take, so just a Wedelin representation is a triple VRN. R is a representation of the Weil group of K, so say K is a p-adic field. This is a representation of the Weil group of K. It's finite dimensional and has open kernel. And N is called the monodromy operator, and it's a nilpotent endomorphism, and it encodes the action of the L part of the tame inertia. So this theorem that I stated here, it's known in the following cases. So, or previously known in the following cases. When n is odd, when n is even, and yeah, pi satisfies a regularity condition, which I'm going to call Shin regular. It's also known as slightly regular in Shin's paper. When pi is square integrable at a finite place. And it's also known in general up to semi-simplification. which means that you lose track of the monodromy operator n. So the goal for today is to extend the compatibility to Frobenius semi-simplification by identifying the monodromy operators on either side. And I should say that this theorem is due to many people. Hopefully, I won't forget anybody. So there's Harris-Taylor, Taylor-Yoshida, Shin, Chenevier-Harris, Clausel. I don't know if I left anyone out. And I want to say a little bit about what the difficulty is in the case when n is even. So in general, you want to prove such a theorem by finding a Galois representation in the cohomology of a Shimura variety, which is associated to a unitary group that has signature 1n minus 1 at one infinite place and 0n at the other infinite places. And if you don't want to impose any additional restrictions on pi, then you want the group to be quasi-split at every finite place. And you can find such a group in the case when n is odd, but it doesn't exist when n is even. So still, Shin finds the Galois representation associated to pi in the cohomology of a Shimura variety for n plus 1 under a regularity condition. And then the compatibility up to semi-simplification is proved by a p-adic deformation argument by Chenevier and Harris. We will work with a Shimura variety which has signature 1n minus 1 at two infinite places and 0n everywhere else. And that will be enough for figuring out what n looks like. OK, so I want to make some definitions. Let's see. So a Wedelin representation is called strictly pure of weight k for some k in R if for some lift of Frobenius, so I should say we're working with, maybe I'll put this here. So we're working with k a p-adic field. OK is the ring of integers. Pi is a uniformizer. OK mod pi is F, the residue field. And the cardinality of F is Q. So we call a Wedelin representation strictly pure of weight k if for some, and then it will follow that for every lift of Frobenius, every eigenvalue of R of phi is a Ve q to the k number. And if X is proper smooth scheme over F, then the Wedelin representation associated with the cohomology of X, the L-adic cohomology of X, is strictly pure of weight I. So there's, I guess, so there's also a notion of mixed. It's mixed if V has a filtration, an increasing filtration, which is finite, and such that,
Excuse me.
yes.
So in your definition, should it be Q the K over C?
I mean, I guess here you can say the absolute value squared. So I'm just going to work with K. Yeah. So if it's mixed if it has an increasing filtration such that the ith graded piece is strictly pure of weight I. So in this case, where something is strictly pure, necessarily n has to equal 0, because n would switch the weight. For mixed, n has to send fill I into fill I minus 2. There is also a notion of pure of weight k, and that is it's mixed. It has all the weights in k plus z. And for every positive I, n to the I induces isomorphisms of the k plus ith graded piece with the k minus ith graded piece. Okay, and it's conjectured that if X is a smooth and proper scheme over K, then the Wedelin representation associated to the L-adic cohomology of X is pure of weight I. All right, and basically what we're going to be doing is finding the Galois representation that we need in the cohomology of such a scheme and proving at least that a piece of that cohomology is pure of weight I. So proving this conjecture in a particular case. Okay, there are some properties of purity that I want to write down. Let's see, maybe I'll write them here. So the first thing is that it's preserved under passing to a finite extension of fields, L over K. So purity is preserved under finite extension. Okay, another thing is that rec of pi, so the local Langlands image of pi, is pure of some weight if and only if sigma pi is tempered for some sigma an automorphism of, for every sigma an automorphism of C. The third property is that given V and R, so part of the data for a Wedelin representation with R semi-simple, there is at most one choice of n which makes VRn pure. So from these properties, well, from properties 2 and 3, we conclude that in order to prove the local global compatibility, we need to show the following two things. So from 2, 3, it's enough to prove A, the fact that the Wedelin representation associated RL of pi restricted to the decomposition group at L, and Frobenius semi-simplified is pure. And B, so if we show that this is pure, that completely identifies the n, we want to identify the n on the local on the local side as well. So we want to show that if pi is conjugate self-dual, regular algebraic, so as above, and y is a place of L, then pi y is tempered. And this is a case of the Ramanujan-Peterson conjecture for GLN. Okay, so the strategy is to prove these two results. And, oh, I should mention that this was proved by Clausel at unramified places. Okay, so the idea is to work with a Shimura variety, which realizes, well, not quite this representation, but its square. So let me. Whose cohomology realizes RL of pi squared. And it will be enough to show that the Wedelin representation associated to this is pure. Okay, and this is associated to a unitary group, which looks like U1 n minus 1 cross U1 n minus 1 cross U0 n to the d minus 2, some number of copies that depend on the degree of the field. So it looks like this at infinity and is quasi-split at all finite places. Okay, and we will find this in the cohomology of X. So, well, I should say such a group exists because the global invariant is nd over 2 plus 2. And if n is even, the degree of the field, we might as well assume it's even. This is even. So such a group exists. Okay, and we want to compute the cohomology of a Shimura variety associated to such a unitary group. In order to do this, we're going to need kind of 3 main ingredients. So I want to write them down. So let's say that I'm going to denote by x as well the integral model for this Shimura variety. And by y, it's special fiber. So one of the results we're going to need is a formula for the cohomology of x with coefficients in some Lie syllabic sheaf in terms of the cohomology of some closed strata inside the special fiber. So So I'm going to call them closed Newton polygon strata. In Y. So I can call them YST, and we're interested in the cohomology of YSTLC, where S and T are parameters for basically Newton polygons. Okay, and so the way this is going to be, so when I say a formula, I mean there will be two spectral sequences. The first spectral sequence will have as its terms these kinds of cohomology groups. It'll converge to another spectral sequence, and that in turn will converge to this. So it's a pretty complicated way of getting to this cohomology from here. But in a sense, this generalizes the Rappaport-Zing spectral sequence for a semi-stable scheme. So we have two spectral sequences which converge to H star of X. All right. Let's see. Maybe I can. So now, given that we're going to have, not just one but two spectral sequences, in order to actually compute something useful, we're going to want a lot of those terms to be 0. So another result we're going to need is D, which says that the cohomology of a closed stratum is equal to, well, at least the pi part of the cohomology, where pi is the cuspidal automorphic representation we started with, is 0 outside the middle dimension. So pi only shows up, if we take pi parts, only one of these will be 0 for only one value of j. This means that both spectral sequences that we have are going to be concentrated on diagonals. And they both degenerate at E1. And the spectral sequence that gives us H star of X LC, when it degenerates at E1, it provides us exactly with the filtration that we're going to need in order to show that the Wedelin representation inside is pure. Okay, and in order to get such a result, we also need a formula for the cohomology of Igusa varieties. These Igusa varieties are going to cover open Newton polygon strata. So we can relate them to these strata. Okay, so the structure of the argument goes as follows. So first we're going to need E, and actually from E we're going to be able to compute relatively explicitly what this is. So we're going to be able to prove the result B right away. So let's see. So the temperedness, we're going to prove it straight from this formula. Then B and E together are going to give us D. D together with a geometric result C are going to allow us to prove A. And then A and B imply the theorem. Okay. And both of these steps, so going from E to B and from E and B to D, are done using computation that is very similar to the style of Taylor-Yoshida. So this is, I guess, the first instance where the monodromy operator was identified, so where purity was proven. And the computation is very similar. OK, so this is kind of the main structure of the argument. And now I'll try to give some details. So we're going to take, so let's say, first I want to talk about how to get the geometric result C. So for that, we take f prime to be a CM field, which is, say, f1e. This is totally real, and this is imaginary quadratic. And such that P splits in E. And we take a prime P above the rational prime P. So f prime and P will play the part of L and Y from the statement of the theorem, except that we can always base change to a finite extension. The reason we can base change to a finite extension is that purity is preserved under. So it's enough to prove purity after such a base change. Then we also take f to be, well, f2e, where f2 over f1 is a quadratic extension, totally real. And such that the prime P splits as P1 times P2. So it splits in F. And the idea is to work with P1 and P2 simultaneously. So usually, I guess when you construct Galois representations and you work with Shimura variety that looks like one, associated to a group that has signature 1 n minus 1 at just one place, you pick a corresponding prime above P. We're going to work with two places simultaneously. And we're going to have two corresponding embeddings. Tau I of f into C for I equals 1, 2. Those would be the two places where the group looks like 1 n minus, has signature 1 n minus 1. Okay. So we can take the base change of the representation of pi from f to f prime, and then maybe put a GL1 part in it. This we're going to call pi 1. And we're actually going to look at kind of the pi 1 part of the cohomology of the Shimura variety. Okay. And we can assume that pi at the place P has Iwahori fixed vectors. Again, since we're just trying to prove purity, and so we can base change to a situation where there are Iwahori fixed vectors. Okay. I don't want to go through the explicit construction of the group G, but so you can find a group G that has signature 1 and -1 at the two places. Associated to it, you can find a PEL Shimura datum, and you can define a Shimura variety, or say an inverse system of Shimura varieties. So X is a system, well, we're going to call it a system of Shimura varieties associated to this group G. And they're all defined actually over the field F prime. That's the reflex field in this case. Let's see. So we can take now, I guess, a irreducible algebraic representation of G. Over QL bar, and that defines a Lie syllabic sheaf. We're working in the case when L is not equal to P. The cohomology of this inverse system with coefficients in ELC has an action of G of the finite adels, and it also has an action of the Galois group of F prime. And it decomposes as a direct sum of pi cross Ri CL of pi. So this goes over representations of G of the finite adels, and this is the Galois part. And here we're going to see the square of RL pi that we're interested in. Okay, and so we're interested in understanding this cohomology. For that, we're going to work with, we're going to define an integral model of X. So, well, let me say U has Iwahori level structure at P1 and P2. XU is going to be an integral model of this Shimura variety, well, with Iwahori level structure. And it's going to be defined over OK, where K is F P1, and that's the same as F P2. We can also think about it as F prime localized at P. Okay, so this will be a moduli space of abelian varieties with various extra structures, such as polarizations, level structure, and so on. And in order to study, say, in order to understand what it looks like, locally you can just look at the deformation theory of the p-divisible group of the abelian variety. And this is only interesting at the primes P1 and P2. So if we take GI to be a PI infinity for I equals 1, 2, and basically, I mean, this is a one-dimensional compatible Barsotti-Tate OK module. And at all the other places, which are at least above the same place of E, the p-divisible group is étale, so its deformation theory isn't very interesting. Okay, so we have these GIs, and now since we're working with Iwahori level structure, this XU will be a moduli space for chains of isogenies Ci, so we start with Gi, that goes to Gi1, and so on, up to Gin, which is isomorphic to Gi modulo the pi torsion. And this works. So this for I equals 1 and 2. OK, and so using basically the same techniques that Drinfeld uses, and we can figure out what the completed local rings of the Shimura variety look like at closed geometric points. So those are just determined by the deformation theory of these p-divisible groups together with these chains of isogenies. So let's see. I'm just going to tell you what the final conclusion is. So we can even extend it a little bit further than just looking at completed local rings. We can get something locally on XU. So I even Zariski locally. So XU is étal over, I'm going to call it XRS, and that is spec OK, x1 through xn, y1 through yn, divided by x1 times xr minus pi, y1 through ys minus pi. So here r and s are determined by the formal height of G1 and G2, the formal heights of G1 and G2. OK, so this is a product of semi-stable schemes. It is no longer semi-stable, but it is log smooth. So, or it can be endowed with a log structure, which makes it log smooth. Okay, we also have some global information about what XU looks like. So for I equals 1, 2, the special fiber Y, I'm going to drop the U, is a union of Y, I, J, where each of these is the closed subscheme where the jth isogeny in the chain Ci induces the zero map on the Lie algebra. Of the group Gi. So an example of such an isogeny would be the Frobenius isogeny. And in general, this property is called having connected kernel. OK, so we can write Y as a union of these closed subschemes in two different ways for I equals 1 and 2. And this is how we can define the strata. So let's say for S and T, just subsets of 1 through n, non-empty. We can define Y sub ST to be the intersection over I and S of Y1I, and then intersected with the intersection over J and T of Y2J. OK. And these strata are proper and smooth over F, and the dimension is 2n minus the cardinality of S minus the cardinality of T. And even more, we can just forget about what S and T are specifically, just remember their cardinalities, and we can form Y L1, L2 to be the disjoint union of Y S T, where S has cardinality L1 and T has cardinality L2. Okay, so our goal is to compute the cohomology of the generic fiber of X through, using the sheaf, just the constant sheaf QL bar supported on these Y L1, L2s. Okay, so let me give some details about that. So we want to understand the action of n on the cohomology of X. So just special fiber, generic fiber with coefficients in QL bar. And we can understand that by studying the complex of nearby cycles on the special fiber. So H star, Y, F bar, QL bar. Oh, sorry. If this was smooth, then we just be fine. But if Y is not smooth, then we have to put here the complex of nearby cycles. In some sense, this remembers cycles from the generic fiber. And the action of n here actually comes from an action of n on this complex. And this is really what we have to understand. Okay, so let me just state the result C, so a precise form of it, and then I'll give some indication for how to obtain it. So there are GK equivariant spectral sequences E1 R m minus R, which is equal to sum from over P minus Q equals R H m Y this converges to what we're interested in. Okay, here I should put YF bar, but if I forget to put it, it should be there. Coefficients in QL bar. ARP side, sorry. Okay. So this will just be.
Do you consider LC?
Yes, that's a very good point. I was going to mention this, but it might as well. So eventually we want to get a formula with coefficients in LC. However, for simplicity, I'm just going to work with coefficients in QL bar. And if we want to obtain the general formula, we're going to have to pick out a piece of the cohomology of the universal abelian variety over this Shimura variety. But the geometry is the same, so I'm just going to work at this level with QL bar. And I should have said QL bar here. Sorry. OK. This is just a spectral sequence that is associated to the monodromy filtration on this complex. So the monodromy filtration is a filtration obtained by convolving the kernel and the image filtration. So the kernel shows up here. We're taking the graded pieces of, so kernel filtration of n. and is nilpotent. So yeah, there's a finite filtration here. This is induced from the image filtration of n. And if you convolve those two, you get the monodromy filtration. Its graded pieces are direct sums like this over p minus q equals r. OK, so this is just standard. However, the next point is that we can actually compute these in terms of the strata that we have. So I'll write the second spectral sequence. So we also have E1 prime. Its general term is k plus 1. So for k plus 1 and minus k plus 1, this is going to be a direct sum from I equals 1 to p plus q h m minus 2k minus p minus q plus 1 of y. So here we're just looking at some strata corresponding to k plus I, k plus p plus q minus I plus 1, with coefficients in QL bar twisted some number of times. And this will converge to hm y grq grp. Okay, so the way in which these two spectral sequences can be useful is that say that we can prove that the first one degenerates at E1 and that each of these pieces are pure of the right weight, then that will give us exactly the filtration that we need in order to show that the cohomology is pure of the right weight. And so basically, we're going to try first to show that a lot of the terms in this spectral sequence are 0. And you can see that, well, if you try to compute the weights of these terms, you'll see that they don't actually depend on p and q, just on p minus q. So that's encouraging because you would want strictly pure when r is fixed. OK, so let's see. Notes. This is just what I've said, but so E1 is the spectral, the one I've written first, is the spectral sequence associated to the monodromy filtration of R psi QL bar. And we can rewrite these spectral sequences with ELK-C coefficients. And this, in some sense, generalizes the Rappaport-Zing spectral sequence. That's, that works for a semi-stable scheme. In this case, we have a scheme which locally looks like a product of semi-stable schemes. OK, so the ingredients in proving this theorem, I just want to mention them briefly. Let's see, maybe. Well, one thing is that we can endow xu over OK with something called a log structure such that it becomes log smooth. So maybe it gets a log structure M such that it's log smooth over OK with its canonical log structure N. And in this case, you can get a very precise computation of the cohomology sheaves of the complex of nearby cycles. So get an explicit description of RK psi QL bar in terms of the log structure M, together with inertial action, which in this case it's trivial. And this follows from results of Nakayama. Another ingredient is that, well, locally our scheme is étale over a product of semi-stable schemes. And there is, Elizy has a product formula for nearby cycles. So the nearby cycles of the product are the derived exterior product of the nearby cycles on each of the factors. So at least locally, we can understand the complex of nearby cycles as a product of complexes for semi-stable. And then the complex in the semi-stable case is very well understood. So I use Saito's construction of the weight spectral sequence in the semi-stable case. Which boils down to understanding very well what the monodromy filtration on the complex of nearby cycles in the semi-stable case looks like. OK. So these are the main ingredients in proving this. And the reason that we get two spectral sequences rather than just one is because we're getting a handle on these cohomology sheaves, but not on the complex itself. OK. So now I want to talk about how to obtain the result D. So we're switching to computing cohomology rather than just nearby cycles. So the result D that we want, more precisely stated, is that, say, the base change away from P of HJYST with coefficients in LC, and then we just take the pi 1 infinity or maybe away from some other primes as well, is equal to 0. So here we have an action of G A infinity, and we base change that. Well, A infinity P. And we base change that in order to get to GLN. OK, so we want something like this. Each closed stratum can be written as a union of open strata. And these, so we're going to call them open Newton polygon strata. These are covered by towers of Igusa varieties. OK. And by computing the cohomology of Igusa varieties using Shin's stable trace formula for Igusa varieties, we can then kind of plug it in here to understand these. Then we'll get an alternating sum in cohomology and understand this. So E is the result we need, a formula for the cohomology of Igusa varieties. I don't want to write it down explicitly because it might be too much detail, but yes, the point is that using the formula E, you can see what part of the, well, you can see a part of the local Langlands image of pi at the place P. You can see the part that lives inside the stratum corresponding to S and T. And I'll explain how you can get from E to B, and it's the same thing to get from E and B to D. So E to B, we need to show that pi p is tempered. So assume pi p is not tempered. Well, one thing is that either way, the local Langlands, so ln k of pi p IL inverse, so the square of the local Langlands shows up in h star of x LC. So since we have, so in order to prove temperedness, it would be enough to show that the eigenvalues of the Frobenius are q to the z numbers. So they q to the k numbers for integers k. And since we have the square here, we can't quite get the eigenvalues of Frobenius, we just get products of them. But still, that's enough information to distinguish two cases. So using classification by Tadic and a result of Jacquet and Shalaika, either pi at the place P is tempered, or, so which is, we're assuming is not happening, or pi p looks like the induction of some term, say pi 1 times some power of the determinant, and that has to be exactly 1/4, because it has to be a half integer once you double it, cross pi 1 det minus 1/4, and then so on. So you can have a pi 2 det to the 1/4, det to the minus 1/4. So either we're in the tempered negative 1/4. Okay. And this 1/4 will introduce an error factor when we compute the cohomology of a stratum. So basically, when we use the formula we have for Igusa varieties to compute the cohomology of the stratum, we get that the base change away from P, H, Y, S, T, Elk C, just the pi 1 part of it, is equal to some constant times the sum of V1, J1, J2 plus V2, J1, J2, shows up twice, plus V3, J1, J2. So also keep in mind that we're in the situation where we have Iwahori fixed vectors. So that tells us exactly what these pi i's have to be. They have to be Steinberg SPSI of chi I for some unramified character chi I. And then what shows up in this stratum is exactly kind of the local Langlands of products of chi J1 with chi J2. So this VK chi J1, chi J2, and then some GL1 part, and then there's this norm to the 1 minus n plus epsilon k. Epsilon k will be the error factor that gets introduced from having this 1/4 here. So epsilon k is either minus 1/2, 0, or 1/2. Depending on whether you have a 1/4 with a 1/4 adding up, or if they cancel, or if you have negative 1/4 with negative 1/4. So we have such a formula. On the right-hand side, the weights are going to be m minus 1, m and n plus 1, just because you can read off the weights from here, and the only thing that changes it is the error factor. So let me write it somewhere. However, the other side, you have an alternating sum of cohomology, and these are smooth, proper schemes over F, so we can compute the weights explicitly. Given that it's an alternating sum, consecutive weights should appear with different signs. On the other hand, here we just have a constant. C is a non-zero constant, either positive or negative. So on the right-hand side, these weights appear kind of the same sign. The left-hand side is an alternating sum. So that gives a contradiction. So the case where pi looks like this cannot occur. So then the only other option is that it's tempered. When it's tempered, again, you're going to have an identity like this. You're just going to have one representation here. That's going to come from a product of characters. You use the Weil conjectures again to compare weights, and that's how you deduce that the cohomology is 0 outside the middle dimension. OK, yeah, I'll stop here.